Hi everyone! This is Professor in Science, and today I want to tell you about quasi-classical states of the quantum harmonic oscillator in another one of our videos on rigorous quantum mechanics. When we think about a harmonic oscillator, what comes to mind is a back and forth motion, for example that of a mass attached to a spring. However, when we think about the energy eigenstates of a quantum harmonic oscillator, for example the ground state Gaussian, they are stationary. This means that they don't describe anything like the oscillations that we have for the classical harmonic oscillator. So the question that we're going to ask today is, does the quantum harmonic oscillator actually oscillate? And what we're going to find is that it does. But we need a coherent state to see those oscillations. Today we're going to explore how the coherent states of a quantum harmonic oscillator are the states that most closely resemble the motion that we observe in a classical harmonic oscillator. And that is why we often give another name to coherent states. We call them quasi-classical states. So let's go! We're seeking quantum states of the harmonic oscillator whose behavior resembles the oscillatory motion of a classical oscillator. So let's therefore start with a quick refresher of the classical harmonic oscillator. I'm going to simply quote the relevant results, but most of you will have encountered this system before, and if you haven't, then any classical mechanics textbook will have the relevant background. First of all, the position of a classical particle in a harmonic oscillator follows an oscillatory motion of amplitude x0 and frequency omega, where the phase phi depends on the initial conditions. Second, the momentum of the classical particle is given by the mass multiplied by the time derivative of the position, which gives this prefactor times a sine function. And third, the total energy of the system is equal to the kinetic energy part plus the potential energy part. Inserting the expressions above for momentum and position, we get this for the kinetic energy and this for the potential energy. We can cancel this mass with this power, and we can then rewrite the whole expression as equal to this common factor, multiplying the sine squared plus the cosine squared. This bracket is equal to 1, and the whole expression simplifies to this constant factor. Therefore, although the values of the kinetic and potential energies change over time, the sum stays constant. And these three quantities here fully characterize the classical harmonic oscillator. What about the quantum harmonic oscillator? Remember that the Hamiltonian H is equal to the kinetic energy plus the potential energy. And we can also write it down in terms of ladder operators or in terms of the number operator. The eigenvalue equation of the Hamiltonian is H acting on the ket n equal to En times the ket n. And the eigenenergies are quantized, where n is a non-negative integer. So how can we connect the quantum oscillator with its classical counterpart? We can describe quantum states in a variety of ways. One example is in terms of wave functions, which capture the extended nature of quantum states in space. This is fundamentally different from the point particles of classical mechanics. However, from the video on Ehrenfest's theorem, we know that the expectation values of operators such as position and momentum can be used to connect the quantum and classical worlds. Therefore, in this video, we're going to look into the behavior of the expectation values of quantum operators and compare them with the motion of the classical particles. The expectation value of the position operator in an energy eigenstate n can be written like this by using the expression of the position operator in terms of the ladder operators. If you cannot remember how to write down the position operator in terms of ladder operators, you can find all the details in the corresponding video that is linked in the description. This calculation requires the expectation value of the lowering operator, and remember that the action of the lowering operator on an energy eigenstate removes one quantum of energy. This means that we get this for the expectation value, which vanishes because the energy eigenstates form an orthonormal set. Similarly, the expectation value of the raising operator vanishes, And these results imply that the expectation value of the position operator vanishes for any energy eigenstate. As energy eigenstates are stationary states, their expectation value is time independent and so basically stays at 0 at all times. We can make an analogous argument to show that the expectation value of the momentum operator with respect to an energy eigenstate also vanishes at all times. For the expectation value of the Hamiltonian with respect to an energy eigenstate, we trivially get the corresponding energy eigenvalue. So let's compare our two scenarios side by side. We have the classical case and the quantum harmonic oscillator in an energy eigenstate. The position of a classical particle in a harmonic oscillator changes according to a cosine, and the expectation value of a quantum particle in an energy eigenstate is always 0. Now turning to the momentum, the classical particle obeys this equation in terms of a sign, and the expectation value of the quantum particle in an energy eigenstate is always 0. Now finally, the classical energy is constant, and the quantum energy in an energy eigenstate is also constant. So what can we learn from this? When we think about the classical harmonic oscillator, what comes to mind is a back and forth motion, for example, a mass attached to a spring. In this back and forth motion, the position here and momentum here of the classical particle change sinusoidally, where the energy here stays constant. For the energy eigenstates of the quantum harmonic oscillator, we also have a constant energy here. But the position and the momentum do not resemble at all the back and forth motion that we expect for a harmonic oscillator. They're both equal to 0 at all times. And this prompts the question of whether the quantum harmonic oscillator is actually oscillating at all. What we will do in the rest of the video is to show that we can make the quantum harmonic oscillator oscillate, but to do so, the system needs to be in the right state. And lo and behold, it turns out that what we need is coherent states. Let's have a quick refresher on coherent states, but as always, you can find full details by following the links in the description. A coherent state alpha is defined as an eigenstate of the Loring operator. Unlike the Hamiltonian, the Loring operator is not a Hermitian operator, so the eigenvalues alpha are in general complex numbers. Coherent states can be written explicitly in the basis of energy eigenstates of the quantum harmonic oscillator, and the resulting expression is that alpha is equal to this prefactor times this infinite sum over the energy eigenstates. We've already seen that individual energy eigenstates behave very differently to the classical oscillator. Coherent states are an infinite superposition over energy eigenstates. And as we'll see today, this precise superposition is such that we will get a motion that does resemble the classical motion as closely as possible. And this is the reason why coherent states are also called quasi-classical states. As we've already done for energy eigenstates, to explore the connection between coherent states and the classical harmonic oscillator, we'll need to evaluate the expectation values of the position, momentum, and energy operators in a coherent state. Before we can do that, we're going to derive a number of expectation values of combinations of ladder operators that will facilitate our calculations in the rest of the video. To do so, we will write again the defining equation of a coherent state, and we also consider the corresponding expression in dual space. To get this, we take the usual approach of turning all kets into bras here and here, all scalars into the complex conjugates here, and all operators into their adjoints. The first expectation value that we want is that of the Loring operator. So using the definition of a coherent state in state space, we end up with alpha. we can use a similar approach to deduce that the expectation value of any power of the lowering operator is equal to alpha to that power. For the corresponding expectation value for the raising operator, we can use the definition of a coherent state in the dual space, and we end up with the complex conjugate of alpha. And similarly, the expectation value of any power of the raising operator is equal to alpha star to that power. The next expectation value that will prove useful is that of A dagger A. We can use the definition of a coherent state in dual space here, and that in state space here, to end up with the absolute value squared of alpha. Next, I want to consider the expectation value of A dagger. In this case, we need to remember from the video on ladder operators that the commutator between A and A dagger is equal to 1. This implies that A dagger is equal to 1 plus A dagger A. Using this result, we can rewrite our expectation value as the sum of these two terms. This is the expectation value above, so we end up with 1 plus the absolute value squared of alpha. This is a summary of the various expectation values that we've just derived. We'll use them thoroughly in the rest of the video, so a good idea may be to take a snapshot or maybe copy them down so that you can easily follow the rest of the derivations. Let's start with the expectation value of the position operator with respect to a coherent state. The first step is to write this out using the expression of the position operator in terms of ladder operators, which is a result that should look familiar from the video on ladder operators. We can then take out the scalar prefactor, multiplying the expectation value of the lowering operator and of the raising operator. From our derivations earlier, we know that this is equal to alpha, and this is equal to alpha star. Therefore, we end up with the prefactor times alpha plus alpha star. Or, using the properties of complex numbers, we can rewrite this as this new prefactor times the real part of alpha. For the expectation value of x squared, we again write it out first in terms of ladder operators, and then we take the scalar terms out as a prefactor, multiplying 4 terms, the expectation value of A squared, the expectation value of A dagger squared, the expectation value of A dagger, and the expectation value of A dagger A. Using the earlier derivations, we know that this is alpha squared, this is alpha star squared, this is 1 plus alpha times alpha star, and this is alpha times alpha star. Putting everything together, we end up with the prefactor times these 4 terms, and this expression simplifies to the prefactor times alpha plus alpha star all squared plus 1. From these results, we can now easily evaluate the root mean square deviation of the position operator in a coherent state, which is given by the usual formula. Substituting our expression for the expectation value of x squared and our expression for the expectation value of x all squared, we then see that we can cancel this term with this term, and we end up with the square root of h bar over 2m omega. And interestingly, the root mean square deviation does not depend on alpha. Let's now turn to the time dependence of the expectation value of the position operator. Let's imagine that the state of our system at time 0 is a coherent state alpha 0. We know that alpha 0 is in general a complex number, so we're going to write it out using Euler's formula as equal to this magnitude times its phase, which I label by phi. We then know from the video on coherent states that the state of the system at a later time t is also a coherent state, characterized by the eigenvalue alpha of the lowering operator, where alpha is equal to alpha 0 times the exponential of minus I omega t. Inserting this expression for alpha 0 in here, we can rewrite alpha as equal to the magnitude of alpha 0 times this phase factor. With this, we can use this expression up here for the expectation value of the position operator to write it at time t as equal to this prefactor multiplying the expression that we just got for alpha and the corresponding complex conjugate. Remembering that the sum of the exponential of I delta with its complex conjugate is equal to 2 times the cosine of delta, we can rewrite our expression as equal to this prefactor times the magnitude of alpha 0 times the cosine of omega t minus phi. Now this form should look very familiar if you've studied the classical harmonic oscillator, but before we discuss this in more detail, let's first look at the expectation value of the momentum operator. The calculation of the expectation value and root mean square deviation of the momentum operator essentially follows the same lines as the one that we just did for the position operator. Therefore, I will simply quote the results, but feel free to give it a go, do the calculations in detail, and it will be good practice. The expectation value of the momentum operator with respect to a coherent state is equal to this prefactor times alpha minus alpha star. It can also be rewritten as equal to this other prefactor times the imaginary part of alpha. For the expectation value of p squared, we get this prefactor times 1 minus alpha star all squared. Finally, putting these results together, we can also evaluate the root mean square deviation of the momentum operator, which is equal to the square root of mh bar omega over 2. And note that this result is again independent of alpha. For the time dependence, we again consider an initial state that is a coherent state alpha 0, and then the state at a later time t is another coherent state alpha, where alpha is related to alpha 0 by this expression. We then have that the expectation value of momentum at time t is equal to this prefactor, multiplying the magnitude of alpha 0 times the sine of omega t minus phi. This final expression probably looks very familiar, but let's look at the energy before we say more. For the expectation value and root mean square deviation of the Hamiltonian, we're again only going to quote the final results, but again, feel free to have a go at the derivation yourselves. The expectation value of the Hamiltonian is equal to h bar omega times the absolute value of alpha squared plus 1/2. The expectation value of h squared is equal to h bar squared omega squared, multiplying alpha to the power of 4 plus 2 times alpha to the power of 2 plus 1/4. With these results, we can also evaluate the root mean square deviation of the Hamiltonian, and we get h bar omega times the absolute value of alpha. The time dependence of the expectation value of the energy is actually trivial. We again consider the state of the system at time 0 to be the coherent state alpha 0, and we then know that the state of the system at a later time t is also proportional to a coherent state characterized by alpha, where alpha is equal to alpha 0 times this phase factor. From this expression up here, for the expectation value of the Hamiltonian, we see that it only depends on the magnitude of alpha. And this means that the expectation value of the Hamiltonian at time t is equal to this. Which means that the expectation value of the energy of the system in a coherent state is time independent. Right, so we compared the classical oscillator with the energy eigenstates of the quantum oscillator at the very beginning of the video, and we concluded that their behavior was very different. We're now finally ready to compare the classical harmonic oscillator with a new family of states of the quantum harmonic oscillator, coherent states. The position of a classical particle in a harmonic oscillator changes according to a cosine. And the expectation value of a quantum particle in a coherent state also changes according to a cosine. Turning to momentum, the classical particle obeys this equation in terms of a sine, and the expectation value of the quantum particle in a coherent state also changes sinusoidally. Finally, the classical energy is constant, and the quantum energy in a coherent state is also constant. So what can we learn from this? While we didn't have the back and forth oscillation that we expected when the quantum particle was in an energy eigenstate, we now see that the quantum particle does indeed oscillate when it is in a coherent state. Comparing the classical position here with the expectation value of the position in the coherent state here, we see that if we identify the amplitude x0 of the classical motion with this expression in terms of alpha 0, it then follows that the classical motion is exactly reproduced by the motion of the expectation value of the quantum particle in a coherent state. Interestingly, using the same relation between x0 and alpha 0, we conclude that the time evolution of the momentum in the classical motion is again exactly reproduced by the quantum motion in the coherent state. So this means that when the quantum harmonic oscillator is in a coherent state, the expectation values of position and momentum oscillate in such a way that they exactly reproduce the classical motion. What about the energy? In this case, we get that the classical energy is equal to the quantum energy minus 1/2 times h bar omega. So energy is a little trickier. Both classical and quantum energies are constant over time, that's right, but the magnitude differs by this term. You might remember that this term is what we called the 0-point energy of the quantum harmonic oscillator, which is a purely quantum phenomenon. For classical oscillators, the magnitude of alpha 0 is much, much larger than the 0-point energy, which means that to a very good approximation, the energy in a quantum coherent state is also the same as the classical energy. Putting all of this together, the coherent states of a quantum harmonic oscillator are the quantum states that most closely follow the motion of a classical particle in a harmonic oscillator. And this is a reason why coherent states are also called quasi-classical states. Coherent states, also called quasi-classical states, are what we need to make a quantum harmonic oscillator actually oscillate. To see this more explicitly, you should check out our video on the wave functions of the coherent states. And as always, if you liked the video, please subscribe.